Welcome to Inside Opt Tutorials. In this episode we're going to talk about transformations. When would you want to convert your input data into other objects? There are really two reasons to do that in Seeker. Number one is when you actually need to turn them into a term. That is, for example, the case when you want to use an aggregator. Aggregators only work on lists of terms, Seeker terms. So then you need to convert your data. And similarly, if you want to index a vector or a matrix, or more generally speaking, a tensor, you will want to transform a list of terms into a tensor object. So with that being said, let's jump right in to the first case, raw data conversion. When you want to convert a general data term, which can be an integer, a float, or a bool, into a term, you simply use the environment function convert. And what you will get back is a term that you can then use, for example, to build a tensor, for example, to build to use in an aggregator. If you have the same thing works if you have a list of those raw data terms, or if you have a matrix of raw data terms, or more generally speaking, if you have a tensor, which is, in this case here, I give a three-dimensional tensor, right? So there's one dimension more than in a matrix. Seeker supports these conversions up to 6 dimensions. So you can have vectors or vectors or vectors or vectors or vectors or vectors of integers, floats, or bools. And the conversion will work. What you get back is the corresponding structure, but instead of having integers or floats or bools inside, you have terms in there. And that is how you convert raw data into Seeker terms. The second case is when you want to index a vector, a matrix, or more generally speaking, a tensor. In that case, you will have to start from a vector of terms. So if you have raw data, you first convert that raw data into a vector of terms, and then you can use the environment function tensor in order to get back a tensor. And there's really only one thing that you can do with a tensor. You can use it as an argument for an index term. And we will see in a moment what that looks like. Again, Seeker supports this up to 6-dimensional tensors. Let's look at an example, the quadratic assignment problem. In the quadratic assignment problem, which contrary to what the name suggests is actually a very linear optimization problem, it's actually not quadratic. You can solve this using a plain old MIP solver if you wanted to. You are asked to place a set of facilities, n facilities, to n different locations. What you know beforehand is the volume of things that you need to transport from each location to the other. This is given in the matrix W. So W tells you how much you need to move from location A to location B, if you look at WAB. And now if you assign each facility a location using the function f, in this case, f of A and f of B gives you the location of the facilities A and B, then the D matrix tells you how far it is. What are the costs of moving one unit of stuff from the first location to the second location, f of A to f of B. And you're supposed to minimize the total transportation cost. So every facility potentially has to exchange goods with other facilities. So this WAB doesn't necessarily have to be a symmetric matrix. But what we do know is that the main diagonal is 0, and in any case, the cost of transporting something from from a location to itself would be 0 as well. So you can assume that the main diagonals are 0. But the W matrix does not have to be symmetric. The distance matrix typically is, but technically it wouldn't have to either. Now, if you wanted to model this problem in Seeker, you obviously need to use an indexing function in order to index the matrix D. So let's look what this looks like in code. Quadratic assignment looks like this. Given is n, the number of facilities, the matrix W, which gives us the transportation volumes, and the matrix D, which gives us the per unit distance costs for each pair of locations. The seeker model looks like this. You create an environment, as you always do, and ideally you already put the environment.end into your code right there, and then you place everything else in the middle. First thing you will want to do is to create a permutation in order to distribute the facilities to the particular locations that you're having. So this is, in this case, the function is called P, not F as before, but it's a permutation of the facilities on the locations. And now you see that we take this matrix D and we convert it. So this is typically a matrix that consists of doubles. We convert it into a matrix of terms, and this matrix of terms we can then turn into a tensor. And we call this tensor seeker D. And now you see how the indexing works. The function index here takes as argument the tensor, and we want to evaluate the tensor at these two, at this row and this column. More generally speaking, this would be a list of indexes that you're using to index this tensor, because the tensor can be up to 6 dimensions long. So this could technically be, if the tensor supports it, a list with 6 different indices as opposed to just 2, but in this case it's just 2 because it's a matrix. And we're indexing exactly as you saw in the formula for the quadratic assignment problem before, the location of facility I and the location of facility J. And we multiply that with the volume that needs to go from I to J. And then we sum this up for everything but the main diagonal. And I'm sorry, this is just the list, right, which gives us that for each pair of ij. And then we sum this up in order to get our costs, and then we minimize the costs. Let's see what this looks like in code. So here we see the example again. We see the first thing we do is get n, w, and d, and also the value of the best known solution, in this case for a particular benchmark instance proposed by Tayar for the quadratic assignment problem. It's called TI30b. It's actually part of a famous set of instances for the quadratic assignment problem. And you see exactly what you saw on the slides. We create an environment, we end the environment, we create a permutation to express that we need to distribute our facilities to the end locations. Then we do the conversion. You see here we take the raw data, which is typically doubles in the matrix D, convert it into terms, and from this matrix we create a two-dimensional tensor, which we call seeker D. And here you see that we do the indexing, get all the summons together exactly as we just discussed, sum them up, and then we minimize this objective function. In this case I gave it 80 seconds, and I told seeker to stop when it reaches the performance of the best known solution for this instance. See here in between that we set a couple of parameters. You know that you can do this. You can set some of the search parameters in order to tinker a little bit with the performance of the solver. This does not replace automatic tuning of the hyper parameterized search that powers seeker. So whenever you have a complete model and a couple of instances of things that you in your operations have to solve regularly, so things that are indicative of what you actually have to do, you should use an automatic tuner for seeker. But you can tinker a little bit to get slightly better performance with it. Then you see that after the optimization, we are spitting out the actual value of the permutation, so which facility goes to which location, the cost, total cost that was achieved, and the number of evaluations that the solver managed to do in the time that it needed to find the best known solutions, or in the 80 seconds, whatever happens first. And then, of course, we finish our environment again. So let's run this. And you see Seeker finishes a little bit after 60 seconds, found the best known solution to this problem, which is 637.117.113. And in those 60 seconds, the solver managed to evaluate the costs of each assignment about 550,000 times. And this is how you use conversions in Seeker to convert raw data into terms, or to convert a list or matrix, or more generally speaking, a tensor of terms into a tensor that gets it ready for indexing.
You're gonna see me shine, 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 walking on beams of light.